The next type of cycle we're going to talk about here is going to be called a refrigeration cycle. Okay, so here we go, refrigeration cycle. The first mistake people make in refrigeration cycle is they spell refrigeration with a D. Okay, there's no such thing. We spell fridge, F-R-I-D-G-E. If you want to use the word fridge, short for refrigerator, has a D in it, but refrigeration does not. I don't know. This is one of those things, one of those weird things about the English language. Okay, refrigeration cycles drive students nuts. Okay, here. I need to explain that to you. Let's draw the same diagram that we did before. Okay, this is going to be our hot reservoir or our high temperature reservoir. And this is going to be our cold reservoir or our low temperature reservoir. And we're going to have a cycle in here. And this is what we're going to be analyzing, is this cycle. And let's see what happens for a refrigeration cycle. Well, here's what's happening. For a refrigeration cycle, we have to plug that refrigeration cycle in. Okay, so we're now going to be adding in, let me change my colors here. We are going to be adding in some power or some work, okay, work to our system. And what that's going to cause is we're going to have that there's going to be heat transfer this way, Q in and Q out. Okay. So we are moving heat from the cold reservoir to the hot reservoir, but we're doing that in a way that there's a cycle inside of here that's able to take advantage of that. So here's what's happening in your refrigerator. This cold reservoir, this here is your refrigerator compartment. When you open up the door of your refrigerator, you're looking in at your cold reservoir, your low temperature reservoir. And what's going to happen is, for example, you have just got done watching a television show, and you have decided that you want to go and make yourself just a really nice piece of pie. Okay, and you have to go and I don't know why you're watching a television show, but that's how it works in this ridiculous story. You watch a television show, you see a pie on the television show, and you're like, man, I really want a pie. So you go up to your kitchen, you make it a nice pastry to put inside of you as a crust, and you fill it up with the apples, and a little bit of cinnamon, and then you put a nice topping on it. Maybe you lattice the top of it, makes it looks really great. You bake it for 45 minutes, and now you eat some pie, and you have your pie. Your pie is done, and you can't eat all your pie, so you put the pie in the refrigerator to save it. Okay, now what happens when you put that pie in the refrigerator? It's warmer than everything else in your refrigerator, and so you want to take the heat away from that pie. You want to take the heat away from that pie. And so that's the Q in. That pie is giving out heat, and that heat is going into the refrigerator. So this portion right here, where the cycle is located right here, this portion right here, this is the actual refrigerator components, okay? The refrigerator components. The compressor, the refrigeration coils, all the lines that you see, the heat exchangers that are inside of your refrigerator. By the way, you could do yourself a favor, go to your refrigerator, see if they're covered if your heat exchangers on your refrigerators are covered in dirt, blow them out with an air compressor, or take a vacuum cleaner and suck that dirt out. Let's increase the efficiency of your refrigerator, or we'll talk about the coefficient of performance of your refrigerator. And then what happens is when it gets done with the refrigeration components, it's blowing out hot air into the back of the refrigerator. If you put your hand behind the refrigerator, you'll notice, hey, it's a little bit warmer back there. That's that hot That's that hot reservoir. Okay? So what's happening inside of your refrigerator is, and I'm not going to go into it right now in detail, but we're taking refrigerant and we are going to be making it very cold through a process. And that cold refrigerant is coming into the cold compartment, and it's going to, your hot pie is going to put heat into that refrigerant and warm that refrigerant up, and it's going to keep going through the cycle. Now it's a little bit warmer. It's going to go back through the cycle, and it's going to then expel that heat out to the back of your refrigerator and come back in and try to get cold again. So it's going through this process like this. Okay. Now here is why I'm belaboring this point. The word of today's lecture is belaboring. We can use the word reject heat in two different ways for this cycle. You can say the refrigeration cycle rejects heat. That's Q out. You can say a pie rejects heat. That's Q in. So you really have to think about the perspective that you're looking at. And I want you, when you're looking at these problems, to be the cycle. You need to be the cycle. And think about what the cycle sees. Okay, what the cycle sees. All right, we're going to do one more thought experiment before I go on here and talk about how we analyze this. Right now, where you are sitting, in your apartment, in your house, wherever it is that you're watching it, you are in, let's just pretend like it's a really hot day outside and your air conditioner is running. You are in the cold compartment of your house, of a refrigeration cycle. Okay, your house, you want to keep your house, it's 100 degrees outside, you want to keep your house at 75 degrees Fahrenheit. That's the cool compartment. You come into that cold compartment, but you are not 75 degrees. You are warmer than that. So you're giving off heat all the time. You're like that pie giving off heat all the time. You have a computer that you're watching, you have something going on. All these things are giving off heat into your house. And if you just let that happen, it will heat up the apartment or heat up the house more than you'd like it to. So what happens is that heat goes out. It goes to the refrigeration cycle, which is probably located somewhere downstairs or wherever you're located in a mechanical room. There's going to be a heat exchanger, and that heat exchanger is going to go connect out to outside. There's going to be that refrigeration unit outside, that compressor unit outside that looks like a big box with a big fan in it. And that's going to be cooling on refrigerant so it can take the heat out of your house. Now, outside of your house where that big compressor unit is, it's blowing out hot air. That's that Q out, that hot side. Okay? So that's what's happening. Again, I'm rejecting heat and the cycle's rejecting heat. We have to think about the wording. The wording on these problems can be very tricky. I encourage you to look at the old test problems I posted and read the problems about cycles and see if you can know, oh, this is a refrigeration cycle. Now that I know it's a refrigeration cycle, let me try to figure out what is Q out and Q in. It's very easy to get those confused if you're not paying attention. All right? Remember when reading these problems, you are the cycle. You're not the pie. You're not the people. You're the cycle. That's how you're analyzing it. Okay, let's look at the equation here. We know for a cycle, the change in energy for a cycle has to equal Q net minus W net. Okay? And we know that this has to go to 0. The energy for a cycle has to go to 0. Okay, that has to be the case. All right? So now let's write what's happening. 0 is equal to, what's our net heat transfer? Well, we're going to have here Q in minus Q out, just like normal. And then we're going to have minus our work net. Well, now our work net is actually coming in to our system. The surroundings are acting on the system. And so we're going to have minus work net. Okay? And I could call this work cycle if I wanted to. So now what's going to happen? These two negatives create a positive, and now if I want to solve this equation, I could say that the work of the cycle is equal to, if this is positive, I have to move these things to the other side of the equation. It's going to be Q out minus Q in. And I want to put magnitudes here to make sure that I've taken care of the sign convention already as I'm working with this problem. Okay, a little different there than our power cycle. A little different than our power cycle. Now we don't measure efficiencies for our refrigerator. We measure something called the coefficient of performance. So the coefficient of performance some books calls this the COP. This book we're going to call this beta. Okay, it's beta. And it is what you want still. It's what you want. All over what you want to give. What you have to give. Now there's a reason why we call it the coefficient of performance. It's not an efficiency. Because this can be, and I'll put this in colorful letters here. This can be greater than 1. Okay, this can be greater than 1. Efficiencies cannot be greater than 1. This can be greater than 1. Okay, that's why we call it a coefficient of performance and not a efficiency. Okay, beta. So what is what we want in a refrigeration cycle? What do we want? Well, we want to keep cool. We want our pie to cool off. We want our bodies to cool off. So we want Q in. What do we have to give for that to occur? Well, we got to plug in our refrigerator. We got to put power to our air conditioning system. We have to give work of the cycle. Okay, and I want to put magnitudes on this so we make sure that that's okay. And this is all on your equation sheet, so you can look at it. Okay, this again, Q in is the heat removed from the people, from the food, etc. That's what Q in is. Now we can write this differently. We can say that beta is equal to Q in. What is the work of the cycle? Well, that's equal to Q out minus Q in. Okay, that's what it can be equal to. Now, again, just like we had in our previous thing, this all could be rates. We could put a dot over all this and do rates, and we would be fine. No problem here. One thing we can't do, a lot of students will say here, they'll say beta is equal to Q in all over Q out minus 1. They'll write this down. That's bad algebra. This is a big no. No, this can't occur that way. So don't make that mistake. Don't do that. The big thing here is beta, the coefficient of performance, can be greater than 1. I can't tell you how many times when we had the luxury of being able to be in the same room together, we would be taking exams. I would have students come up to me and they would raise their hand in exams and they would call me up and they say, Dr. Wakeland, I'm doing this problem and I'm calculating the coefficient of performance and it's greater than 1. And I know it can't be greater than 1, so I don't know what to do. And I would have to tell them, I look at their exam paper and I would say, and they have everything right, but they have forgotten that the coefficient of performance can't be greater than 1, and so they're panicking. And what sometimes they'll do is they go and reinvent thermodynamics and go find a way that, oh, I got it, I figured it out. And what it ended up being was they would just mess it all up. They had the right answer, they just didn't understand that coefficient of performance could be greater than 1, and so they got themselves all screwed up, and they made the answer incorrect. I'm going to encourage you not to do that. I'm going to encourage you to understand what's happening, that coefficient of performance can be greater than 1. Notice how I'm saying this over and over and over again because this is such a common issue. And I want you to know, more importantly, what does Q in represent What does Q out represent? What does the work of the cycle represent? Those are important. This equation is dead easy to use. It's just plug and chug. But unless you know what to plug in it, the chugging gets all messed up. So please understand that. That's what we need to talk about for refrigeration cycles.